Hello, dear students. Today we are going to conduct the new lecture of Physical and Inorganic Chemistry CH 401 Coordination Chemistry. Next slide. Slide. The content of this chapter is given here as a double salts, coordination compounds, coordination complexes, and complex ions, coordination numbers, unidentate, bidentate, and polydentate ligands, chelating ligands, and chelates, physical methods used in study of complexes, nomenclature of coordination compounds. Full screen. Full screen. Yes, the content that we have been seen. Now, coordination chemistry is a modern chemistry of this inorganic chemistry, and it is the branch or important branch of physical chemistry and inorganic chemistry, which studies the coordination compounds or complexes. These compounds are widely distributed in minerals, plants, and animals, and in atmosphere also. A coordination compound contains central metal ion, and around that central metal ion, number of negatively or neutral molecules are gathered together. And here, this Alfred Werner prepared many coordination complexes and studied their physical and chemical properties. Now, the next addition of molecular compound, addition or molecular compound. Now, say coordination compounds are additional or molecular compound. Addition or molecular compound means are two or more molecules gathered together so as to form the bigger molecule, and which is nothing but the addition or molecular compounds. Now here, these are of two types: double salts and coordination compounds. In this double salt, there are addition compounds which exist in only solid state but dissociate into their constituent ions in aqueous solution, and the double salt lost their identity in the solution. For example, say suppose potash alum. When this potash alum is dissociated into the water, then you will see that it will dissociate into the constituent ions. Likewise, this more salt, carnallite. What does it mean? Now here you will suppose these two compounds, when they were gathered together or added together along with the water, then it will form the potash alum. And this potash alum is a double salt, stable only in the crystalline form, and when they are added into the water, they can be dissociated into their individual ions. Say suppose K plus, Al plus, SO4 minus, means what? They lost their physical and chemical properties when they are dissociated into the aqueous solution. Now the second one is a coordination compounds or complex salts. Now here in this coordination or complex salts, what happens there? When these type of compounds, when added into the aqueous solution, they retain their identity and they do not get dissociated into their constituent ion, and they will not give the property of that constituent ion. For example, say suppose this cobalt ammonium chloride or nickel ammonium chloride or potassium ferrocyanide, when this nickel chloride and ammonia, they are added together, it will form the purple colored crystal, and these crystals are of nickel ammonium chloride. Similarly, APCN ferrocyanide and potassium cyanide, when they are added together, they will form potassium ferrocyanide. Now see this nickel ammonium chloride or potassium ferrocyanide, when they are added into the water, then you will see that it will dissociate into one positive and negative ion, but they cannot be get dissociated into as a nickel plus, as a ammonia, or as a separately chloride, and they retain its property into the aqueous solution. Now, what is the difference between the double and coordination compounds? Now, double salt exists only in solid state and dissociate into their constituent ion. Here, coordination compounds exist in crystalline as well as they will not dissociate into or the coordination compound exist in crystalline as well as in solution also. They lost their identity in the solution, and this coordination compound do not lose their identity in solution. Complex ion is absent, complex ion is present. Complex ion is absent, complex ion is present. Physical and chemical properties are the same as the that of constituents, and here in the coordination compound, physical and chemical properties are different as that of original compounds. Examples are listed here. Examples are listed here, and examples are listed here. Now, some definitions that we want to go through. First one is a complex ion. It is a electrically charged ion which consists of central metal ion or ion surrounded by a group of ions and neutral molecule. For example, suppose central metal ion is a nickel, and neutral ions are this ammonia, is surrounded by 6 NH3 molecules, neutral molecules. Likewise, here in this second example, platinum is a central metal ion, and ammonium molecule or 4 ammonium molecule and chloride molecule, 2 chloride molecules are surrounded to this nickel. Central metal ion, the cation. Now here in this first example, we have been seen that nickel and platinums are a central metal ion. The cation to which one or more neutral molecules are coordinated is called as a central metal ion. It is always present in square bracket. Now see here, copper ammonium ammonia, central metal ion is a Ce2 plus, and surrounded by the 4 NH3, and likewise some examples are listed here. Molecular or non-ionic complexes, the complexes which do not contain cation and anion, or which do not separate into the cation and anions, are called as the molecular compound. Now here see the chlorocobalt ammonium. Here you will see that the charge on it is a 0. Here nickel CO4 are the molecular complexes, and the charge on the molecular complexes is 0. Ligand, the group of neutral molecules or ions that are maybe negative ions, ions that are directly coordinated to the central metal ion in coordination compounds are called ligand. The ligands are bonded to the central metal ion through coordinate bond, and are always present in the square bracket. Now here see, here this is a square bracket, COCl3 NH3 thrice. Here this is a CO is a central metal ion, this Cl3 is a ligand, and NH3 is also a ligand. Now here you will see that 3Cl minus and 3 NH3 are the ligands. Classification of ligands, depending on the number of electron donating centers or the number of dative bonds formed with the ligand, are classified into 3 types: monodentate or unidentate ligand. It donates or it has only one pair of lone pair of electron, and coordinate to the central metal atom or ion by one atom. For example, say suppose here F minus, here you will see that valency is a 1, here is a valency 1, here is a valency 1, here is a valency 1, and by this way these are the monodentate or unidentate ligand. For example, say suppose now second one is a bidentate ligand. If the two electron donating centers are there or two donor atoms and forms two dative bonds, here you will see that ethylene diamine, what it is there, here these are the two electron donating ammonia. Here also what it is there, glycinate. Here also two electron donating groups are there, as here is a ammonia and here is a oxygen. Bidentate ligand, it has a two electron donating centers. Now here two examples who have been seen. Now the third example is a oxalate ion. Then fourth example is a dimethyl glyoxime. Here you will see that one and two electron donating centers are there. Here also two oxygen electron donating centers are there. And here in this carbonate ion also two dative bond or two electron donating centers are there. Polydentate ligand, when the same ligand is coordinated to the central metal ion by more than two donor atoms. Now here you will see that two atoms or by more than one dative bond, then it is called as the polydentate ligands. These tridentate, these are the tridentate depending upon the number of ligand. If three ligands are there, then the tridentate. If four ligands are there, tetradentate. If five ligands are there, then pentadentate, or if six ligands are there, then hexadentate. Now here different examples are listed here. Here see, you will see that tridentate, which is nothing but a diethyl triamine, 1, 2, and 3 electron donating centers are there. Here also in the tetradentate, 1, 2, 3, and 4 centers are there. And by this way, these are the depending upon the electron donating centers, what it is there, depending on electron donating centers, different what it is there, the polydentate ligands can be classified. Now next is there, here also the hexadentate ligands are there. Then coordination number and legency. Now coordination number, the number of ligand which are directly bonded to the central metal ion atom or ion in a coordination compound is called coordination number, and the of the metal or ion. Now you will see that here is the central metal ion is a nickel. How many ammonium ions are there? 6 ammonium ions are there. Therefore, the coordination number is a 6. Here also you will see that nickel is a central metal ion, and ethylene diamine is a there are 3 what it is there are there, and therefore 3 and the charges are +2, and therefore what it is there here is a depending upon, because it is nickel is a +2 charges, and that's why here is 6 coordination number is there. Then different coordination number, depending upon the coordination number, the geometry can be decided. How the geometry can be decided? If 2 coordination number is there, then the geometry of the complex it will be the linear. Then if 4, then tetrahedral. If 5, then trigonal. If 5, then octahedral. Coordination number is a characteristic property of the metal. Some metal may have different coordination number. Now see, this silver and aurium has a 2 coordination number. Then this copper, nickel, and cobalt. Now you will find that though the charge is 1, still it has a 2 coordination number. Though the charge is 1, the 1 positive charges, still there is a coordination number is 2. Now here you will see that copper 2 plus coordination number is 4, then nickel, then cobalt has a coordination number 4. Likewise, Fe2 plus, Fe3 plus, Ni2 plus, Cr3 plus has the coordination number 6. Now what is next is there chelating ligand and chelates. When bidentate or polydentate ligand is attached through 2 or more donor atom. Now see, here 2 donor atoms are there to the same central metal ion forming the ring structure. The ligand is called as the chelating ligand. What does it mean? That is, when this central metal ion, what it is there, central metal atom or ion forming a ring structure, the ligand is called as the chelating ligand, and the complex formed by the chelating ligand is called as the chelates. Now here you will see that here the bidentate ligand acting as a chelating ligand. Then next is there here the second example is there copper, and here this copper you will see that 1 2 3 4 5 and 6. Likewise the chelating metal chelate is formed. Now the complex formation, the general reaction may be this monodentate ligand, then the negative charges, then it will form the metal complexes. Then here in the chelation, what happens there is this metal, then ligand forming the ring structure, and therefore complex formation. Likewise, then in the chelation, if this ligand acting as a ring forming agent, then the complexes are called as the chelate. The chelating ligand form more stable complexes than ordinary unidentate ligand, and the process of formation of chelate is called as the chelation. Charge on the complex or complex ions. The charge on the complex or complex ion is detected by adding the individual charges of the reacting metal and ligand. Now, in this complex, if the ligand is there, then if central metal ion is also there, then if you want to decide the charges, then you will have to add that central metal ion atom in it. Neutral complex is formed when zero valent metal is surrounded by the neutral ligand. Neutral complex, now see, CO is a zero valent. Here is a CO is a zero valent. CO is a zero valent. Then this is a neutral complex. The central metal ion is surrounded by enough number of oppositely charged ion. The neutral complex, the in the neutral complex, the algebraic sum of individual charges is equal to the zero, while in case of complex ion, the algebraic sum of individual charges is equal to the charge on the complex ion. In neutral complex, it is a zero. Then in other complexes, the addition of charges may be positive and negative also. All the metal ion in their carbonyl have zero oxidation state. Then alkali metal in their stable compound have the oxidation state +1. Alkaline earth metal have the oxidation state +2. And therefore ligand with minus charge, -1 charge, as a chloride, bromide, iodide, and number of examples are there. Ligand with -2 charges, that we know. Then neutral ligand, NH3 is a neutral ligand, water is a neutral ligand. Then other ligands are there. Example, calculate the charge on ApCO5 as now see ApCO5. Let the charge on the Ap is you want to calculate the charge of central metal ion. Charge on the central metal ion, then ligand ligand with a -2 charge, calculate the charge on the central metal ion. Then suppose for example carbonyl 5, then let the charge on Ap is a x and the charge on the CO is a 0. Then we know that right now we have been seen in complexes, the charges can be calculated as an algebraic sum of the all charges. Then what it is there, the sum of charges of Ap and 5CO ligand is a 0. What it is there, because it is a neutral complex, what it is there, it is the neutral complex, and for that purpose what it is there, the total charges are 0. Then Fe plus 5CO is equal to 0. Then X is equal to current because charge on CO is also 0, then AP is equal to 0, and therefore this charge on this AP in that complex is 0. Here APCN6, another example, let the charge is on AP maybe X that we want to calculate, and the charge on Cl minus is a minus 3. And here you will see that it is a minus 3 charge on the total complex, and therefore AP plus 6 Cn minus is equal to minus 3, and therefore X plus 6 into minus 1, because the charge on the Cn is always minus 1, and it will be uh, X minus 6 minus 3, and therefore the charge on the central metal ion AP here in this complex is a 3, and by this way the charge on the central metal ion can be calculated for the complex's coordination sphere. The central metal ion with the molecules or ion coordinated to it constitute the coordination sphere. While writing the formula of the complex ion, the central ion along with its coordination group is written inside the square bracket. Simply that coordination complexes are written in the square bracket, as you will see here. Such a square bracket will be there. Here you will see the square bracket. Physical method used in the study of complexes. Now the physical method, because if you want to, you have prepared the complexes, then you will have to study for that complexes what sort of these. Then the to study the complexes, some methods are there, and the first method is a conductivity measurement. The electrical conductivity of a solution of ionic compound depend on, that we know, the conductivity always depend on the concentration and number of charges present, maybe positive and negative, or the number of ions present in that solution, that will affect on the conductivity. That is, in this method, 1 molar solution of known or unknown compound is prepared, and their molar conductance is compared. From the total number of charges, the sum of charges on the cation or anion furnished by the one molecule of the compound can be calculated. For example, suppose if you prepare the sodium chloride solution, it contains Na plus and Cl minus ion, because the total charges are 2, and the molar conductance of it is what it is there. The molar conductance of it is a 114 Siemens. Then barium chloride, 4 molecules are there, that is 2Ba2 plus and 2Cl minus. Here also lanthanum chloride, here also cobalt chloride, 4ANS3. Then you will see that the conductivity will depend upon here 2 ions, 114 conductance, then 4 ion increases, then 6 ion increases, and you will see for the 2 ions it is a 102 Siemens or Mo. Cryoscopic method measurement. It involves measurement of freezing point of the pure solvent and solution. The freezing point of pure solvent is lowered. The freezing point of pure solvent is lowered when solute is dissolved. That we know, because we have studied in the first semester. That is, when you put the non-volatile solute into the pure solvent, then of course its freezing point is lower, and the lowering or depression of freezing point is a qualitative property and depends on the number of particles present, that we have seen that relation. The molecular thus it is possible to know the molecule dissociate and the number of particles formed by one molecule or compound on dissolution in the solution. For example, say suppose NaCl gives nearly twice the depression in freezing point expected for unionized salt. This is because it gives the 2 particles we have seen there in the lowering of freezing point. That is, the solute should be non-volatile, and if it is a volatile, that is 2 types of solutes are there. That is what it is there, that electrolyte and non-electrolyte. Here NaCl is a electrolyte. It gets dissociated into the ion in aqueous solution, and for that purpose, what it is there, the freezing point expected from the unionized salt is doubled to that of uh, non-ionized salt. This is because it gives the 2 Na plus and Cl minus. Same way, here it is a 3, then LaCl3 will give nearly 4 times the normal depression in a freezing point. Thus, by measuring the molar conductance, we obtain the total number of charges. By stereoscopic measurement, we obtain the number of particles. By combining these two information, we can determine the structure of various components. For example, say suppose COCl3, 6NH3, number of particles are 4, then its a molar conductance is 300, then number of charges are 6, that is the number of charges are 6, and the structure of the complex will be like this. Then same way the for this compound, and by this way it is decided, the structure can be decided by the study of cryoscopic measurement. Then here it is a spectroscopic measurement. Electronic spectra, UV or visible, provide the valuable information on the energy of orbital and on the shape of complex. It helps to distinguish between tetrahedral, octahedral complexes and whether the shape is regular or distorted. Then X-ray diffraction method, X-ray determination of this crystal is the most powerful method, and this provides the detail of the extra shape, bonds, length, and bond angles of the atoms in the structure. Then magnetic measurement, the measurement of magnetic moment susceptibility gives the number of unpaired electron present in the complex, and from the knowledge we can decide the arrangement of electron and which orbital are occupied. This helps to reduce the structure of complexes. The complex nickel ammonium nitrate shows square planar as well as octahedral structure first when mu is equal to 0, that is the dipole moment is 0, all electrons are paired and the complex is square planar with dsp2 hybridization and represented as nickel ammonium nitrate. Then structure second, when dipole moment is a 2.84 Bohr magneton, then it indicates the presence of unpaired electron, and the complex is octahedral with D2sp3 hybridization and represented as likewise. Then writing the formula of the complex. While writing the formula of the complex ion is enclosed in a square bracket that we know. The metal ion is surrounded, represented first, and then coordinated group are listed in the order negative ligand first, and then neutral ligand and positive ligand, alphabetically according to the first symbol within each group nomenclature. Now see, suppose KBr, potassium bromide, then here potassium hexacyano, or it is there, potassium hexacyanoferrate. Then here in the molecular or non-ionic complexes, what it is there, diamino, what it is there, chloroplatinum chloride. And the oxidation state of the central metal ion is shown by the Roman in the bracket parenthesis at the end of the name of the complex with a space between the two. For negative oxidation state, it is a minus sign given in the bracket is used, while for zero oxidation state, likewise 0 is used. Then what it is there, hexamine cobalt chloride. Here now you can see that 2 chloride ion, then 2 minus charges. Here the 2 positive charges will be there on the cobalt, and therefore hexamine cobalt has the 2 positive charges, and here it is written in the bracket after the name of the central metal ion. Here also nickel, then tetracarbonyl nickel. Now you will see here tetracarbonyl nickel. Nickel has a 0 because it is a neutral complex. Here it is a sodium tetracarbonyl oxalate. Then here it is a -1 charges on the cobalt, and In naming the coordination sphere, the ligand are named first and then central metal ion. In naming the coordination complex, ligands are named first and then central metal ion. The ligands are named in the alphabetical order, irrespective of their being neutral, negatively, and positively. Means what? First neutral, then secondly negatively, then after that positively charged ligand. Then, for more than one kind of simple ligand, prefix like di, tri, tetra, penta, hexa, hepta, octa are used while for the complexes of same kind of prefixes. Then the oxalate, sulfate, hydrogen, then nitrate, then complex ligand. If there are complex ligand, then en, diene, triene, benzene, aci, then cyclopentadienyl, likewise, or DMZ, etc. Whenever necessary, the point of attachment of ligand to the central metal ion is directed toward the central metal ion. Now you will see that is this NO2 group, nitro group is attached to the central metal ion. You can write nitroso, then here nitrito, because two negative one negative charges, then cynato, thiocyanato, then thio, you can write also thiocyanato N also. Then pentamine nitroso N salt. Now if suppose then pentamine nitroso cobalt, and what it is there, cobalt, then pentamine nitroso N cobalt, then the third ion. Geometrical isomers are designed by using cis and trans isomerism. What it is there? Trans designation. Now these are also the coordination compound. Then what it is there? Diamine, dichloro platinum can be written as like this. Here it is a two ammonia molecules are on the same side. Therefore, what it is there? This is a cis, and two ammonium molecules are on the opposite side. Then it is represented as a trans. Extra and levorotatory optically active compounds are designated by positive and negative. These are also optically active compounds are also coordination compound. Then if it is levorotatory, then dextrorotatory or levorotatory, then dextrorotatory is a positive and levorotatory is a negative, or represented as a D and L. For the ligands having long complicated name, abbreviated in short forms as ethylene diamine in, ethylene diamine, then pyridine PY, ethylene diamine tetraaceto, that is ETTA, then glycinato, GLY, then acetylanato, then ACAC, then dimethylglyoxime, DMG. For ligand, which acts as a bridge between the two metal two metal atoms, the Greek letter mu is written their names. What it is there, and the prefix mu is referred before the name of each kind of bridging atom. Now see here, mu amino, mu amino, mu nitro N. Now these are the two central metal ions. What it is there? Two central metal ions, and this is a ligand. Then mu amino, mu nitroso N, oxy amino dicobalt, third nitrate. Isn't it? And by this way, this is the criteria for assigning or the structure name of the coordination compound, and for a ligand also. And this is the content of this coordination chemistry. And here we are going to end the coordination chemistry. Next time we will see the next chapter of this CH401, of inorganic, which is attached to the physical chemistry in CH401 as a physical and inorganic chemistry. Here we will stop our presentation, and here we end our presentation.